Good morning. Today we're going over our practice exam 3. Again, this covers how we classify reactions, how we quantify reactions, and then why reactions occur. So let's get started. This is a little bit of a shorter test because there's a lot of math in it, and that math takes time. And so you could expect about 20 questions over the span of those 3 chapters. And hopefully this gives you an idea of what the distribution is going to be, but it should be about 1/3 from each of the chapters. So first we're looking at precipitation, valid precipitation product for this reaction. It says I've got an aqueous solution of sodium carbonate, and remember, I think I told you this, you're going to have to be able to put these together. This is what comes from your former exam, your last exam on ionic compounds. You need to remember that sodium is +1 and carbonate is -2. So sodium carbonate is actually Na2CO3. I told you it was aqueous. I'm reacting it with an aqueous solution of calcium chloride. Calcium has a charge of +2. Chlorine has a charge of -1. So I'm going to need 2 chlorines to make that work. And I told you that was aqueous. And products you're going to have to predict. And remember, these are ionic compounds, but the cations always react with the anions, and vice versa. So you always get the outside ions with the inside ions. So sodium with a 1+ with chlorine with a 1+ is going to give me sodium chloride. And calcium with a 2+ and carbonate with a 2-. That's really nice. That's going to give me just calcium carbonate. And now the question is, which is the valid precipitation product? And according to our solubility rules, which you must memorize, all group 1 ions are soluble, so that would definitely be soluble. And neither calcium nor carbonate are on our list of things which are soluble, so we're going to assume that that is our solid precipitate. So this is the answer they're looking for, calcium carbonate, right there. Next, the following may be classified as oxidation-reduction reaction. Identify which species is reduced and explain why. Okay, so if we're looking at this, we've got C2H6 plus O2 goes to form CO2 plus H2O, and we're going to assign oxidation numbers in order to determine what was reduced, what was oxidized. So according to our rules for assigning oxidation numbers, which you must memorize, when I'm looking at covalent compounds, I'm going to follow the rules. So rule number 1 is fluorine gets to be -1, but there is no fluorine here. So rule number 2 is hydrogen gets to be +1. So there's a hydrogen, it gets to be +1. And then I can move to the rule that says the sum of oxidation numbers has to equal the overall charge. Since the overall charge is 0, then that's going to be 2, because I've got 2 carbon atoms, times whatever carbon is, plus 6 times whatever hydrogen is, which is +1. So I have a +6 plus 2 times something has to equal 0. That tells me that the carbon must be -3. 2 times -3 plus 6 equals 0, right? Now oxygen here is elemental. The rule says any atom in its elemental state has an oxidation number of 0. And for our product here, I've got 2 covalent compounds, no fluorine, no hydrogen, so the next part of that rule says oxygen gets to be -2. Since there are 2 of those, that means this carbon must be +4 to offset that. And here I get to assign the hydrogen first since it's higher priority. There's 2 of them at +1, meaning that 1 oxygen has to be a -2. Now that I've assigned oxidation numbers to each of these species, I could tell what was oxidized and what was reduced. And what I do is I look for what changes, right? So carbon is -3 on this side, and now it's +4. Hydrogen is +1 on both sides, so it didn't change. And oxygen is, in both cases, -2. And then we remember that oxidation is losing electrons, and reduction is gaining electrons or becoming more negative. This is becoming more positive. So it looks like oxygen became more negative because it went from 0 to -2. So that was reduced. And it looks like carbon became more positive. It went from -3 to +4. So it was oxidized. And now they wanted to know what was reduced. We decided it was the oxygen because it was gaining electrons. Just like that. Next, identify the oxidizing agent in the following reaction. We're going to play the exact same game that we just did here. We're going to say we've got KCl plus silver nitrate goes to form potassium nitrate plus AgCl. Okay. And for ions and ionic compounds, oxidation number is the same as ion charge. So what we see, because this is group 1, potassium +1, chlorine's -1, that's the charge. Silver is always +1, and we would also know that because the nitrate has a -1 overall charge. But for the nitrogen and oxygen, I have to assign these individually based on the rules for covalent bonds or covalent compounds, because polyatomic ions are held together with covalent bonds. So there's no fluorine, there's no hydrogen, but there is an oxygen. Oxygen gets to be -2. There are 3 of them, so that's -6. So the nitrogen has to offset 5 of those 6 in order to give the nitrate an overall -1 charge, or in order to give the whole compound an overall neutral charge. Potassium is still +1. This nitrate is the same as that nitrate, so we can go through that process again, or we could just recognize that they're the same. That saves us some time. And silver is +1 because chlorine is -1. And then I look for what changed. Potassium is +1, +1. Chlorine is -1, -1. Silver is +1 on both sides. Nitrogen is +5 on both sides. And oxygen is -2 on each side. So everything stayed the same. Nothing actually changed. And that tells us that nothing was oxidized and nothing was reduced. So there is none. This is not an oxidation reduction reaction. Next, a solution of potassium hydroxide is mixed with a solution of magnesium iodide. Which of the following species is a spectator ion? Okay, I'm going to write this out. Potassium hydroxide mixed with magnesium iodide. Now potassium is +1 and hydroxide is -1. Magnesium is +2 and iodine is -1. That means I'm going to need 2 iodides to make that work. So I've got potassium hydroxide. This is magnesium iodide. How could I possibly know what's going to be formed? Well, I know that the cations react with the anions and vice versa. So insides and outsides. I get potassium with iodine +1 -1. It's formula Ki. And then I get magnesium with hydroxide +2 -1. I'm going to need 2 hydroxides there. And I'm going to need more space here. Okay. And let's see, we've got 2 solutions. These are aqueous solutions. Potassium is always soluble. Magnesium is always soluble unless, and this is not one of my exceptions, so these are soluble. Potassium is always soluble, so that will be aqueous. And neither magnesium nor hydroxide are on our list of things which are soluble, so we could presume that that is the solid precipitate. Now we've described this reaction adequately, we can say, what is a spectator ion? So a spectator ions are ions that are present on both sides and are not involved in the reaction themselves. So if I remove what changed in the net ionic equation, this is a solid, so it's not an ion on both sides because it's a solid on this side. So, and that was formed from magnesium and hydroxide. So that's the net ionic equation, is that magnesium reacts with hydroxide to make magnesium hydroxide. And these then, because this is aqueous potassium, this is aqueous iodide, this is still aqueous potassium and iodide, those are our spectator ions. So either potassium or iodide would be correct. Of course, only one of those is listed. It would never make you choose between 2 right answers. So we'll say potassium is our spectator ion. All right. Next, solution of aqueous hydrochloric acid. I'm running out of space here. Aqueous hydrochloric acid is mixed with a solution of lithium hydroxide. hydrochloric acid, H is +1, chlorine's -1, lithium's +1, OH is -1, so I know I've got the right ratio there. And in my product, outsides react, insides reacts with H with OH, makes HOH, which is also known as H2O. Hopefully you recognize that as a liquid. And Li, which is +1, with Cl, which is -1, gives me LiCl, and group 1 ions are always soluble, so that, there we go. If we play the same game, we say what changed, what's going to be in the net, what's going to be a spectator. You can see aqueous, aqueous, liquid, aqueous. So this is part of the net ionic equation. This is part of the net. This is part of the net. And that's a spectator. That's a spectator. These are spectators because you've got aqueous chloride, aqueous lithium, and aqueous lithium, and aqueous chlorine still. All right, so these are my spectators. These are my net, the parts to my net ionic equation. So which is going to be present in the net ionic equation? The answers could be H+, OH-, or H2O. And of course, I'm not going to make you choose between more than one. So only one of those is going to be present. And here it is. There's a hydroxide. All right, oxidation number of sulfur and calcium sulfate. What we're going to do here is note that this is first off an ionic compound between the calcium ion, which is in group 2, and the sulfate ion, which is polyatomic ion we memorized has a charge of -2. Because the sulfate is a polyatomic ion, it's made between two nonmetals, these are held together with covalent bonds, and so we need to use the rules for covalent bonds to assign oxidation numbers. So if there's no fluorine and there's no hydrogen, then we look at the oxygen and say that that gets to be -2, and there are 4 of them. So 4 times -2 plus whatever the sulfur is has to equal the overall charge, which in this case is -2, and hopefully you'll see that that's x plus a -8 gets to be -2. X must be +6. So the sulfur is +6, the oxygen's -2, calcium is +2. So they want the sulfur +6. Okay. And last question on this section. Which is produced in an acid-base reaction? Well, your acid is your H, and your base is your OH, and you produce water. H plus OH makes water. That's our acid base. So that's what we're looking for. Right, on to chapter 6. If I balance this, what is it going to be? Calcium hydroxide plus H3PO4 goes to form calcium phosphate plus H2O. 1 calcium on the left, I've got 3 on the right, so I'm going to need a 3 here to start. I'm not going to balance the oxygen because I have oxygen everywhere. I'm going to wait on that. And I'm not going to balance the hydrogen either because it's in 3 different spots. But I could go and I can balance the phosphorus. In fact, I can balance the whole phosphate. I've got 1 phosphate there, 2 there, so I'm going to need a 2 here. So these 3 have been balanced against each other for calcium and for phosphate. So now I can look at the hydrogen that's left over here, and I've got 3 times 2 is 6 hydrogen atoms, plus 6 hydrogen atoms gives me, I'm going to need a 6 times 2 to balance out the 12 hydrogen atoms. And now I'm going to hope that oxygen falls into place. These oxygens are already accounted for because they're part of the phosphate. But here I have 3 times 2 is 6 oxygen atoms, 6 oxygen atoms, so that's it, I'm done. For the fully balanced reaction, there should be a 6 in front of the water. There we go. How many molecules are present in 4.25 moles of CCl4? The key is to remember that 1 mole of anything contains 6.022 times 10 to the 23rd of that thing. And you don't even have to remember that because I'll give it to you. So if you know the number of moles, 4.25 moles, of this case CCl4, And then 1 mole of anything, including CCl4, contains 6.022 times 10 to the 23rd molecules of that thing. And I plug this in. .25 multiplied by 6.022 times 10 to the 23rd. Put that in exponent notation. I get 2.56 times 10 to the 24th molecules of CCl4. Next, what is the molar mass of magnesium hydroxide? I'm going to have to pull up a periodic table for this. Here's my periodic table. I need magnesium and hydroxide. I'm going to zoom in here. Hopefully you can see magnesium is 24.31. And hydroxide is OH, right? And I've got O, which is 16. I think. There it is. And H, which is 1.008 right there. And before I just add that up, I need to make sure I've got the right formula. This is very important. Magnesium is +2 because it's in group 2. And hydroxide is polyatomic ion I memorized. It has a charge of -1. I memorized that too. So if I put that together, I'm going to need 2 hydroxides. That's going to affect the molar mass that I add up here, because I need 1 magnesium plus 2 hydroxides. That is 2 oxygens and 2 hydrogens. So that gives me a molar mass of 58.32 grams per mole. If I don't have the right ratio of hydroxide to magnesium ions, I won't get the right answer. And note that you're going to have to convert between names and formulas in order to do that. So don't forget that material we covered on our last exam. Next, what is the mass of this many moles calcium nitrate? Let's clean up some space. We're looking at calcium nitrate. And if we know the number of moles and we want grams, we need the molar mass. So again, to our periodic table, we see calcium is 40.08. We said that oxygen was 16. Nitrogen, I believe, is 14.01, but you can always look it up. So a molar mass of 1 calcium plus, I hope you can see, 6 oxygens there and 2 nitrogens. Gives me a total molar mass of 164.1. Now I plug this in. If I have this many moles, I could use dimensional analysis. I'm going to put this on the bottom. No, 164.1 grams calcium nitrate in 1 mole calcium nitrate. I've got to do it that way so moles will cancel. I'll be left with grams, which is what they asked before. Should get a mass of 88.3 grams. Next, going the other direction, if I have the grams, then can I calculate moles? Of course I can. This is just dimensional analysis and looking stuff up on the periodic table. So if I have Rb2C2O4, rubidium, carbon, we know that oxygen is 16. We can look up on our periodic table. Carbon is 12.01. And rubidium right here, 85.47. Okay, so we add that up. We have 2 rubidiums at 85.47 each, plus 2 carbons, 12.01 each, plus 4 oxygens at 16 each, gives us a total molar mass of 258.96 grams per mole. Okay, and they said if this is the number of moles I have, so I start with what I'm given, 1.43, sorry, number of grams I have. Grams, Rb2C2O4. And now grams will have to go on the bottom to cancel that out. And 1 mole. Grams cancels. That gives me moles, which is what they asked for. 1.43 divided by 258.96 gives me 5.52. There it is. Almost didn't see it there, but it's there. Times 10 to the minus third. Okay. If I balance this equation, then what does 2 moles of H2 do? Well, let's balance the equation first. P4 plus H2 goes to form PH3, okay? And I've got 4 phosphoruses here, so I'm going to need 4 phosphorus atoms there. That gives me 12 hydrogen atoms here, so I'm going to need 6 times 2 is 12 hydrogen atoms there. So now they're asking me what happens if I have 2 moles of hydrogen atoms. So 2 H2s gives me what kind of result? Okay. Well, I know that what I've got here is 6. So if I have one of these reacts with 6 of those, then let's see how much P4 it will react with. 2 H2s. 6 H2s react with 1 P4. That means I'm going to have 1/3 of a P4. So I have 2 here. It's going to be 1/3 here. And if I have 2 H2s and 6 H2s make 4 PH3s, then 2 times 4 is 8 divided by 6 is, let's see, 4/3 or 1 1/3. Is that right? That sounds kind of, my brain is telling me I might be doing it wrong. 2 times 4 divided by 6. Nope, I was doing it right. 1 1/3 moles of that. Okay, so would 2 moles of H2 react with 2 moles of P4? No, it only reacts with 1/3 mole of P4. Does 2 moles of H2 produce 4 moles of PH3? No, it only produces 1 1/3 moles of PH3. Would it not react with phosphorus at all? No, of course it reacts with phosphorus. It just reacts with less of it. Will it react with 1 mole of P4? Nope, it only reacts with 1/3 of a mole of P4. And would it produce 1.3 moles of PH3? Yes, that's 1 1/3 moles of PH3. That's what it will do. Okay, mathematically, according to the formula that we came up with. Okay, now a gram to gram conversion. Now I can do this because I'm really good at it, but if you're having a hard time knowing kind of where to start and where to end, then please, please, please take advantage of the conversions roadmap that is given to you on the test. I give this to you on the test. And what this does is it tells you how to do these problems. If you know where you're starting and where you're ending, you can do these problems. So let me kind of zoom in on just that roadmap. Okay. So they're giving us this equation. Carbon dioxide produced in the reaction of this with that to form that and that. First thing I'm going to do is write that reaction down because the words are not terribly helpful. But if I have C2, H2 reacts with oxygen to form, that means I'm going to form products, CO2 and H2O. Okay, CO2, H2O. Oh, this is a combustion reaction. All right, and they're telling me that I start with 30.4 grams of CO2. That's not what I started with, but that's the number that they give me to start with. And they want to know how many grams of H2O. So in other words, I've got this reaction going. This is how much carbon dioxide I get, how much water would have to be formed in the same reaction. And so the first thing I did was write this out. The second thing I'm going to do is balance it. 2 carbons, I need 2 carbons, 2 hydrogens. I have 2 hydrogens, excellent. And here I have 4 plus 1 is 5 oxygens. So that is going to be, if they come in pairs, that's going to have to be 5 halves or 2.5. And that tells me I have to, everything's balanced, but in order to have whole numbers, I'm going to multiply everything by 2. So this is going to be 2, 5, 4, and 2. And I can verify 2 times 2 is 4 carbons, 4 carbons. 2 times 2 is 4 hydrogens, 2 times 2 is 4 hydrogens. And now I have 10 oxygen atoms on the left. That's 8 plus 2, so I did that right. Okay, so I've got the balanced equation. They've got grams. They want to know grams. And I'm like, I don't know how to do that. I don't remember. This is where the conversions roadmap comes in. And you see what I have is grams of one thing, CO2. I have given to me 30.4 grams CO2. And what they want is grams of something else. How many grams H2O? So if I look at the roadmap, where do I have grams? Grams and grams. I have grams of A and grams of B. What's A and B? It's just a stand-in for anything. So grams of any one thing and then grams of any different thing because A is different from B. So I'm going to define, and it doesn't matter whether I call this A or B, but I'm going to say CO2 is my A and H2O is my B. So they gave me grams of A and I want grams of B. So they gave me grams of A. I'm starting here. That's my current location on the map because this is a map. They want grams of B. That's over here. So this is my current location. This is my destination. And the map tells me how I can get from grams of A to grams of B. It tells me exactly what to do. It says, hey, you should start with a molar mass of A and convert that to moles of A. Oh, okay, I could do that. A is carbon dioxide, right? So if I start with 30.4 grams carbon dioxide, which is A, grams of A, use the molar mass of A. Okay, I'll look at the periodic table. Carbon is 12.01, oxygen is 16. So my molar mass of carbon dioxide, 2 times 16 is 44.01 grams per mole. So that's the molar mass, and that's going to get me to moles. So CO2, 44.01 grams per mole. And that's going to go on the bottom. The roadmap doesn't have to tell me that because I can see that grams need to cancel. Right, so grams of A cancels, and now I'm at moles of A was carbon dioxide was A. So now I'm at moles of A. Hey, that's exactly where the roadmap told me that I would get if I used the molar mass of A, starting from grams of A. So now I am at moles of A. Now the roadmap says, hey, you can go from moles of A to moles of B if you use the coefficients of that balanced equation. That's what we recommend that you do because there's not really any other route to get you where your destination is. So let's look at the balanced equation. I have A, moles of A is right here because we said this is A, and we said H2O is B. So the coefficients of the balance equation going from A to B, it says 4 moles of A will react, or 4 moles of A are produced when I produce 2 moles of B. So here we go, 4 moles carbon dioxide for every 2 moles of water. And again, this doesn't tell you what to put where, because dimensional analysis tells you, hey, you've got to put moles of carbon dioxide on the bottom to be left with moles of water. So those will cancel. So this was our A. And now, hey, look at that. We are at moles of B. That's exactly where the roadmap told us we would end up if we used the coefficients of the balanced equation. Next, now that I'm at moles of B, the roadmap says, hey, you should use the molar mass of B, and that'll leave you at grams of B. And that was your destination, right? This is where you started. This is where you wanted to go. That's the only route that'll take you there. So the molar mass of B, I can look at that up. I know hydrogen is 1.008 from my periodic table. Oxygen is 16. So H2O is going to be 18.016 if I plug that into my calculator. Grams per mole. And dimensional analysis tells me I better put that on the top. Grams of H2O. Every 1 mole of H2O. So my moles will cancel. And I'll be left with grams of H2O, which was, I said, H2O was B. So I'm left with grams of B, and they wanted grams of B, so this is where I stop. So the roadmap tells you how to get from any one point to any other point in these stoichiometry conversions. Additionally, it'll help you know when to stop, right? Because there's all sorts of conversions you can do all over the place. And we're going to be adding to this as we get ready for our next exam. And so I highly recommend you use it, because it'll help you remember, like, oh, no, I got what I was looking for. I should stop now. So let's put this in. 30.4 grams of carbon dioxide divided by 44.01 grams of carbon dioxide per 1 mole of carbon dioxide, multiplied by 2 moles of water divided by every 4 moles of carbon dioxide, and then multiply that by 18.016 grams of water for every 1 mole of water, and I get 6.22 grams of water. Right there. That's it. Okay. This is almost the same type of question. I'm starting with 5.34 grams of this. We want to know how much of this I form. It says theoretical yield. You can see they want grams. So they give you grams of one thing, and now they want grams of another. We call that the theoretical yield, because you might not actually get that much. But let's write this out. Fe2O3, oops. Plus aluminum goes to form aluminum oxide plus iron. And if I balance this equation, which I should always be doing, 2 irons, 2 irons, 2 aluminums, 2 aluminums. I've got 3 oxygens on both sides. That's good. And they're telling me I've got 5.34 grams of this. And they want to know how much iron, how many grams of that. So I'm going to say this is A and this is B, just for convenience sake. And my roadmap says if I want to go from grams of one thing, A, to grams of another thing, B, then this is the route that I need to take. So it says I should start with the molar mass of A. Okay, I can do that. Molar mass of Fe2O3. I know the oxygen is 16. Fe, look that up, I think it's 55. Let's see, where are you? There you are, 55.85. Okay, so 55.85 times, oops, start over here, times 2 plus 16 times 3 gives me a total molar mass of 159.7 grams per mole. So if I'm running this on the roadmap, I start with grams of A, 5.34 grams, Fe2O3. Use the molar mass to convert to moles. That's going to have to go on the bottom. Grams per mole. So my grams cancels. Now I need to use the coefficients to go from moles of A to moles of B. I have 1 mole of A for every 2 moles of B, or 1 mole Fe2O3 for every 2 moles of Fe. Now I'm at moles of B. I use the molar mass to convert to grams of B, and we know that Fe is 55.85. So let's put this here. We have 55.85 grams of Fe. Every 1 mole of Fe, moles of Fe cancels. And I can plug this in. 5.34 divided by 159.7. Multiply that by 2. Multiply that by 55.85. We see that I should get 3.735 grams of Fe. That's it. Next, I've got another equation, pretty similar. I'm preparing NH3 from N2 and H2. Okay, so N2 plus H2 goes to form NH3. And it says NH3 is prepared from 28 grams of N2 and excess H2, so I've got enough of this to go as far as I want. It tells me the theoretical yield of NH3 is 34 grams, so I don't have to calculate that. That's nice. When the reaction is carried out, I only get 20 grams, so this is theoretical, and the actual equals 20 grams. And they want to know what the percentage yield is. What's the percent that I got? Well, the percentage is the actual divided by the theoretical. Multiply that by 100. So this is not going to be used. All I need is the actual and the theoretical. But you have to know what you're doing in order to know that this is not going to be used. So let's plug that in. Actual of 20 divided by theoretical of 34. Multiply that by 100 to make it a percent, and I get 58.8% for that equation. All right. Now we're moving on to Chapter 7 material, and we're looking at the collision theory. Which statements describe it? Uh-oh, look at these little squares. That's different from these little circles. That means I can select more than one, and I do say more than one statement may be correct. So watch out for that. We're not looking for just one statement, but everything that is correct. Let's see, reactant particles, they must interact in specific orientations. Yes. Must be hot to begin the reaction process. No, although an increase in temperature can increase the rate, but not all reactions have to be hot. Reactant particles do need to collide. Yes, atoms don't do long-distance relationships. Reaction must be exothermic. No, reactions can be endothermic. And lastly, catalyst must be present. No, some reactions will go faster with a catalyst, but not all reactions require catalysts. So these are the two that are consistent with the collision theory, which says atoms or particles have to collide. They have to collide in specific orientations, and they have to collide with sufficient energy in order to overcome the activation energy in order to react. So those are the two that are included here. In this reaction, how would we describe it? The sign of delta H is negative. I hope you can all see that. So that narrows it down to here. Is the reaction exothermic or endothermic? Delta H negative, that means exothermic by definition. In this case, what quantity of heat produced if 90 grams are consumed? Okay, this is just another stoichiometry problem. Let's see. We have C3H8 plus 5O2 goes to form 3CO2 plus 4H2O plus 488 kcals. And we're doing 90 grams of C3H8. So we'll start there. 90 grams C3H8. We need the molar mass, because this is for 1 mole. Makes 488 kcals. So carbon was 12.01, hydrogen 1.008. Again, you don't have to memorize these. I just happen to have them off the top of my head, so I could do that. Get a total molar mass of 44.094 grams per mole. Plug that in here. 44.094 grams C3H8, 1 mole C3H8. And now we see 1 mole makes 488 kcals. So here we go. Let's cancel. We can plug this in. 90 grams divided by 44.094 grams in a mole. Multiply that by 488 kcals in a mole, and I get 996 kcals will be produced. Okay. Following reaction is spontaneous at 25 Celsius, which best describes the thermodynamic changes at this temperature in the process given. Okay, so we want to know about delta H, delta S, and delta G. And you don't have to memorize this equation. I will give it to you, but this is what's going to be helpful. Delta G equals delta H minus T delta S, right? This is if it's spontaneous. This is the heat. This is the entropy or disorder. And spontaneous would mean favorable, would be negative. And we were told that it's spontaneous. Hey, they told us that. So we know that the delta G is negative. And looking at this reaction, I have 3 moles of gas going to form 2 moles of gas. It's a combination reaction. So I am forming fewer molecules. I'm becoming more ordered. That tells me that delta S is negative because I'm becoming more ordered. I have fewer product molecules. So this is favorable because it is spontaneous. But more order is actually unfavorable, which means that even though we don't know anything about delta H, nothing is given us, we can predict that in order for this to happen at all, I've got to have a favorable delta H, because this is not helping me react at all. Okay, so this has to be favorable. In other words, it has to be negative. So delta H is negative, delta S is negative, and delta G is negative. This because they told us. This because we can deduce it based on what we see, and this because we can deduce it based on what we know about how entropy and enthalpy work together to determine if something's going to be spontaneous. Next, we want to select the energy diagram, which has a slow reaction with a large negative free energy change. So negative free energy goes from high to low, and they want a big one. So this would be a large negative free energy change. And a slow reaction has a really big activation energy. So this has large negative free energy, but it would be a fast reaction. This would be a slow reaction, but that's a very small negative free energy change. This looks like it fits the bill. Large activation energy, large free energy change that's negative. Both of these are positive free energy changes, so that's the only one that's going to fit with what I described. Next, what describes the way a catalyst works? This is one of your homework questions. Catalysts make reactions go faster, and since the rate of reaction is based on the size of your activation energy, then in order to make it go faster, it must lower that activation energy. So decreases the value of the energy of activation. All right, equilibrium expression K. It's going to be products raised to their coefficients divided by reactants raised to their coefficients. So we're looking for NO squared times Br2 divided by NOBr squared. That looks like this one. Excellent. Position for the equilibrium of a system where K is 4.6 times 10 to the negative 3. That's much less than 1, so that's going to be favored to the left, or reactants. The concentration of products is relatively small, so the left and small. So that is to say reactants goes to form products. Of course, if we're looking at equilibrium, your K is your products divided by your reactants. And if your K is really small number, then that means that this is large and this is small. And that's what's going to give you a small K value. So favored to the left, and products relatively small. Last question. For the following reaction, increasing the pressure would cause the equilibrium to do what? This is one. We had a couple of homework problems just like this. And we said that here I've got 2 moles of gas, and here I have 1 mole of gas. And gases take up space. So increasing the pressure says I don't have as much space available, right? Increasing the pressure. So I'm going to move to wherever I'm taking up less space to compensate. So 2 moles of gas takes up more space than 1 mole of gas. So I'm going to move this direction to compensate for the less space that I have because I was increased pressure. So it's going to shift to the right towards product. Let's see how we did. Perfect. That's it. I hope that this was helpful. Have a nice day, guys.